Hey everybody, next exercise is on similar triangles. Now, similar triangles have the same shape, but they are different sizes. So in the example in the book, we've got two triangles here, and if we have a close look at this, we can see that the angles are equal, the corresponding angles are equal. But then when we look at the sides, the corresponding sides, we can see that side there is 6. The corresponding side to that is that one there, which is 2. So that's got a scale factor of 3. The 2 has been multiplied by 3 to get 6. That side there, the corresponding side to it is 5. It also has a scale factor of 3. 3 5s are 15. And the last side, 12. And 4 also has the scale factor of 3. So each of the three sides have been multiplied by 3 in the small triangle, so therefore it is similar. Our similar side, we write the notation for this is triangle ABC is similar to triangle XYZ. Okay, you could copy that down and then we'll move on and have a look at the next slide. Now the first example, you have to find the values of x and y in similar triangles CBA, XY, Z. Now in this example we're told that they are similar, so we don't have to prove that they are similar. Now the corresponding angles here are angle Y corresponds to angle B, angle Z corresponds to angle A, and angle X corresponds to angle C. Notice that the order is different. It's as though the triangle's been flipped over, in fact. Now then, the side that's corresponding to 5.4 then is actually 3.6. It's between the dark and unshaded, the shaded and unshaded angles, shaded, unshaded. So it's the side between those two angles. Y is between the dot and unshaded, so dot and unshaded, so it corresponds to the 4.9. The X corresponds to shaded and dot, so shaded and dot, so it corresponds to 2.3. Okay, so we can work out the unknowns by doing ratios where one of the sides is the unknown. We can only do one at a time though. So in the solution that they've provided here, they've written that xz, so x to z, corresponds to C to A. So y over 4.9 is equal to 5.4 over 3.6. See that they're corresponding sides. We make y the unknown by multiplying 5.4 by 3.9 and dividing by 3.6. They've done that a rather long way around, haven't they? Anyhow, it basically works out to be 7.35. And similarly, we do the same for x. Okay, y to z, that's x, corresponds to B to A, which is 2.3. And 5.4 corresponds to 3.6, xy to CB. Once again, I don't know why they take a long way around to do this. Really the easiest way is just to multiply that side by 2.3 anyhow. And that works out to be 3.45. So why don't you copy that one down as well, and then we have a look at the the next example. Okay, it's not another example, it's the tests. So here are the three tests for similar triangles. Two triangles are similar if three pairs of corresponding angles are equal, three pairs of corresponding sides are in proportion, in other words they have the same scale factor, two pairs of sides are in proportion and their included angles are equal. So that's the three tests for similar triangles. Okay, let's copy that one down. Now, in this example, you've got to prove that triangle XYZ is similar to triangle WVZ. Now, what we need to remember here is that this side corresponds to this side, and that side corresponds to that side. So in the solution then, side XZ over ZV, so that becomes 15 over 35, simplifies down to 3 over 7. The other pair of corresponding sides here are YZ over ZW, 6 over 14, which simplifies down to 3/7. So those two sides there are in proportion. And the third point here is that these two angles here are vertically opposite angles, so they're the same size. So that fulfills one of our conditions to show that they are similar. So therefore they are similar triangles. Now just look at the proof here. Since two pairs of sides are in proportion and their included angles are equal, the triangles are similar. And also they wrote down vertically opposite angles here as well. So just remember that when you're doing these proofs. Okay, so let's copy that one down, and we move on and have a look at the next example. Now the next part is on the ratio of intercepts. Now, so the following result comes from similar triangles. If you can imagine these transversals here, if you can imagine that they were extended to produce a triangle. So if we extended that up to there like that, and we extended that line up to there like that, we've got this triangle, a big triangle here, with these smaller triangles superimposed on it. So there's that triangle there, and then there's that triangle there, and then there's that triangle there. Now, because these three lines here are parallel, and this has a common angle up the top here, these angles here are going to be the same, these angles here are going to be the same, so therefore the three triangles are similar. And so therefore the lengths of these sides, the intervals between the parallel lines, are going to be proportional to each other. So we can write this as a ratio A to B to B to C equals D to E to E to F. Or we can write those as fractions. AB over BC equals DE over EF. Now let's have a look at the first example. We've got to find the value of x. So using our ratios of intercepts, we write x over 8.9 equals 1.5 over 9.3. Then they do this annoying thing again. All you have to do is multiply the other side by 8.9 and you get the answer. So x is equals 8.9 times 1.5 over 9.3. I really don't know why they do that. But anyhow, it works out to be 1.44. Okay, so let's copy that one down, and then we'll have a look at the next example. Now you have to evaluate x and y to one decimal place. Now in the solution here they say use either similar triangles or ratios of intercepts to find x. You must use similar triangles to find y. We'll have a look at that one in a second. Now, if you just use ratios of intercepts, we can write that as x over 5.8 equals 2.7 over 3.4. Okay, and hooray, they've figured out how to do the shortcut. They've just multiplied that by 5.8. That brings it down to 4.6 to one decimal place. Now, similar triangles. So the main thing here is, if you can imagine, this shape here is actually made up of two triangles. Let's draw these over on the other side here. Okay, so let's draw some lines. Okay, imagine you've got two triangles here. Whoops, a bit longer. Oopsie. That's your small triangle there, and then that's superimposed on a bigger triangle like this. Okay, more or less the same. So they're similar triangles. That side there is that side there, and so on. That side there is 3.4, but that side there is 3.4 plus 2.7. Okay, so now to find y then, so you got y over 7.1 is equal to 2.7 plus 3.4 over 3.4. Okay, the big triangle over the small triangle. So 2.7 plus 3.4 is the big triangle. The small triangle is just the 3.4. So you've got y over 7.1 equals that, and they've managed to multiply the other side by 7.1, and then that simplifies down to 12.7. So just remember, when you see something like that, is really imagine that it's two triangles superimposed on each other, and because these are parallel, because this angle up here is common to both of them, therefore they will be similar. That angle equals that angle equals that angle. Okay, and that's pretty well it for similar triangles. Have a go at the exercises, mainly pick on the hard ones, but make sure that you can do them all. Okay.